So how do stars shine? Well, stars are giant nuclear reactors. They convert hydrogen into helium in their core. They're sort of like a thermonuclear device, a hydrogen bomb, except controlled. They are actually controlled by their magnetic fields. If we could figure out how to do that on Earth, we could actually have a fusion reactor, sort of like Doc Brown in Back to the Future. But it turns out that making a bomb is a lot easier than controlling that reaction. But stars don't have to worry about that because of their intense magnetic fields due to their large size. So, a star is born from a cloud of gas and dust called a nebula. And so any given nebula has enough material to make thousands of stars. And due to the force of gravity, gravity will start pulling together little bits of this nebula. Think about little buds on a flowering plant. Think about taking some dough and pinching out little pieces to make cookies out of. And one of these little pinched areas where gravity is pulling it in will continue to get hotter and hotter and hotter as gravity pulls it in. And the question is it going to get hot enough to do fusion or not? That's the dividing line. And the answer to whether it gets hot enough depends upon how massive it is. You know that when you're cooking and you take dough and you don't pinch enough, you don't get a good cookie. Well, the same thing with making stars out of the nebula. If gravity doesn't pinch together a large enough bit of nebula dough, then it's not going to collapse enough to get hot enough to start nuclear fusion. In nuclear fusion, we have to take protons and we have to slam them together and get them to fuse. And the problem is that protons have a positive electric charge. And as you hopefully have learned, positive charges or two like charges are going to repel each other. Opposite charges attract. So when you try to slam these two protons together, they're going to be like, nope, nope, get away, don't like you. We have to overcome that. So we need to have a high enough pressure. We need to have enough gravity. We need to have enough mass to slam them together and get them to fuse. So if we don't have enough mass, we can't get a high enough energy, and we can't do that. So how much mass does this forming protostar have to have so that it will actually get hot enough to achieve nuclear fusion? It turns out that that has to be at least 8% the mass of the sun. If it is smaller than 8% the mass of the sun, then it will not become a star. It will continue to collapse until it cannot collapse any further, and then slowly cool off and be a failure. Hashtag failed star. We call a failed star a brown dwarf. A dwarf because it's small. Brown, again, historically, reasons for lots of bad names in astronomy. They're actually more of a magenta color because they shine in infrared, because they have some heat, but they don't have enough energy to actually glow, to actually shine. All right? So if this forming object has at least 8% the mass of the sun or more, it will be able to slam together those protons with enough pressure to actually get them to fuse and form helium. And this has to happen in the core of the star because that's where the pressures are highest and that's where there's the highest energy to slam these protons together. Okay? So, once this fusion has started, it will continue until all of the hydrogen in the core has been exhausted. And remember in our discussion of the HR diagram, the stars that are born with more mass are hotter and brighter, but they use up their fuel faster. Hopefully now that makes more sense to you. Yes, they're born with more fuel to begin with. Like the Lamborghini has a larger gas tank than our smart car. But that doesn't overcome the fact that it's burning that energy so much faster. So, hydrogen gets converted into helium. 4 protons, 4 hydrogen nuclei, get converted into 1 helium nucleus plus energy. Where does the energy come from? The energy comes from the most famous of all equations in science, E equals mc squared. This comes to us from Albert Einstein's special theory of relativity. That's the one that says you can't travel faster than the speed of light. Sorry, Star Trek. E is energy, m is mass, c is the speed of light. The speed of light's a big number. When you square a big number, you get a really big number. Think of this like when you go to the airport and you're traveling abroad and you have to exchange your money. I know you always end up losing in the deal somehow, probably because of those fees that you have to pay. But depending upon the currency, a certain amount of dollars equals a different amount of British pounds, for example, versus euros. Because this rate of exchange is so high, a little tiny bit of mass gets converted into a tremendous amount of energy. Well, where does that mass come from? If you actually put on a scale the 4 hydrogens that go into the reaction and the helium that comes out, you would find that the 4 hydrogens actually have more mass than the 1 helium. Where did that mass go? It was converted into energy. E equals mc squared. Now, there are 2 different processes that stars can use to convert hydrogen into helium. The first is the way that the sun does it. This is something called the proton-proton cycle. It's basically just the protons slamming into each other and making helium. But there's a more efficient, effective way that heavier stars can convert hydrogen into helium. And this is called the carbon cycle. I know it's confusing because we're not making carbon, we're converting hydrogen to helium. Carbon acts as a catalyst. If you remember from maybe high school chemistry, a catalyst is something that helps the reaction go. So in stars that have a higher mass, as long as they have carbon in them, the carbon acts as an enabler, as a helper, and it helps the hydrogen combine to form the helium. But the carbon is not exhausted. The carbon sticks around and helps more hydrogen become helium. And that is how stars shine.